Hi, Prabha. Let me know when should I start. Hello?
This is Vasant Raju. So I'm going to chair this session.
Okay, yeah.
So still participants, shall we wait for another couple of minutes?
No problem. Just let me know. But everything, you can see my screen and everything, right?
Yeah,
Okay.
we can see your screen.
Okay.
Yes. So your lecture is going to be 1 hour 20 minutes.
Mm-hmm.
So how would you like me to give a reminder? Means at what time? At 10 minutes before?
Yeah, 10 minutes before. And I am okay if people want to ask questions in between. So I don't know how it is being done. So will you be monitoring
Yeah.
the chat box or
In
something?
the morning session, they were taking the questions.
Yali, I'm not able to hear anything.
You're not able to hear anything. Oh, but I was just talking to Vasant Raju and
Hello?
No. It's audible. It's audible.
Yeah, we
Yali
can
is
hear
audible.
Prabha. Are you able to hear me now? Hello?
Anyway, I can hear.
Okay. Yeah, because I won't be able to see the chat boxes. There is something here. I can see, but I won't be.
No, your voice audible. Everything is
Okay.
fine. YouTube also live.
Okay.
And the part 1 and part 2, are you going to cover in this lecture itself? How?
Yes, if something is left over, if there's a spillover, then I will take the last half an hour of the tutorial part.
Okay, thank you.
Or it will be used for Q&A from the students, whatever it is. Huh?
Yeah, okay. And if all the participants have attended, there is an announcement. There is an attendance sheet has been shared by Dr. Crispin to all of you. So please sign it. It means it will be open till end of T session. That is till 4:10. Okay. Okay, I think there are 190 participants. You please go ahead, start with your lecture.
Okay. Thanks, Vasant.
Yeah.
So good afternoon, everyone. I am Piyali Chatterjee. I also work at the Indian Institute of Astrophysics. And I would be giving the second part of the solar physics lecture. So normally in the month of May every year we have this summer school in the Kodaikanal Solar Observatory. You can see this lecture hall over here. So we usually have our lectures here, and it's on the top of a hill, and if you go down the hill, so there is this place where people can mingle over coffee and tea. So I really miss the summer schools in Kodaikanal. It's a really cool place, both literally as well as figuratively. And this is the tunnel telescope here. So as the situation may be, let's just bear with this virtual online event, which the organizers have put together, which is a really difficult part to do with so many participants and all these things. So thanks to the organizers for having this event in place. So I will be giving my talk in two parts, roughly divided into solar atmosphere and MHT waves, which is related to the quiet sun phenomena. Whereas in the second part, I will have more energetic events like flares and CMEs. So you can ask questions in between, and we will see how things go. So it's not necessary for me to finish all the material, but you can stop me and ask any questions at any point in time. So yeah, so these are some of the reference books if you want to read more about solar physics. And here is my email ID and my web page, and you are welcome to visit those if you want to know more about my research. And these are some of the references you can start with. So for if you want to learn more about MHD, this is the number 3, Physics of Fluids and Plasmas, is an easier book to read. And if you want to be a little more rigorous, then you can go for the School's Road book. And if you want to know about the sun, I mean, a good book to start is with this one by Michael Stix. And then you can read about, physics of the solar corona. That's also a nice, really nice book. And specific MHD specific to the sun, you can have in this very famous book by Eric Priest. So in the last lecture by Rajguru, you would have learned about the solar interior, helioseismology, little bit of the dynamo process, and he might as well have left you at the photosphere of the sun. I am guessing that. So this is the typical image when you look at the photosphere through the Swedish solar telescope, which has a 1 meter aperture. And then you see these granulation scales, which are indicative of solar convection. And then you have these cooler regions known as sunspots here. So these sunspots, each sunspot has an umbra, which is a more darker region, where the magnetic fields are predominantly vertical and surrounded by what is known as a penumbra, which is a more diffuse region where the magnetic fields are more horizontal than vertical. So these are also known as active regions because they are groups of sunspots. For example, this big sunspot is probably has probably 2 spots inside it. We'll come to know more about this later. And then there are these smaller regions called pores, which are emerging active regions, emerging sunspots. This is the size of the Earth to the scale. And on the right, you see a simulation of solar granulation done by my PhD student Shohel. So here you see this granulation pattern that may be occurring in a very small box here indicated, where these green regions are the regions where the magnetic field is organizing itself. So it's not just simple convection, but the convection occurring in presence of the magnetic field. So it is also known as magnetoconvection. And when the magnetic fields become stronger, then they assemble themselves into sunspots. So when we want to go outside this, outside the photosphere, so far you have learned about the interior. So we will take off outside the surface of the sun after this. So we have to learn a little bit about, how the temperature and density structure of the sun appears as. So here you may have already seen these plots. So this is a approximate plot of temperature versus the height above the photosphere. So the height is given in kilometers here. And this solid line is how the temperature changes. So this is the height equal to 0 is approximately the lower photosphere, where the temperature is 6,000 Kelvin. And then if you go above it, say 500 kilometer above it, you find the temperature minimum. And after that, the temperature keeps on increasing till it reaches about 1 million Kelvin in the solar corona, which is about say 2,000 to 3,000 kilometers above the photosphere, already above the photosphere. And this dashed line here indicates the plasma density. You can read off the values of mass density from the right-hand side. So there's the temperature and the density. And the different regions are also demarcated approximately. So this is the photosphere till the temperature minimum. And after that, it is the chromosphere. And then there's a transition region that there's a very sharp rise in the temperature, the kinetic temperature. And then you have the corona, where the corona is supposed to be very hot. And when I say the temperature of the corona, you would already know that it is not the Planck's black body temperature of the corona, but it is rather the non-equilibrium temperature or the kinetic temperature of the plasma in that region. So whereas still the photosphere or even in the chromosphere, the sun can be thought to be emitting a black body spectrum. Whereas, when you go really high up, the density also has a steep decrease. The plasma is really rarefied, rarefied. And so you cannot have equilibrium, thermodynamic equilibrium anymore in these regions. And hence the temperature, the definition of temperature is not the Planck's black body temperature at 1 million Kelvin. And the way these temperatures are estimated are by looking at, by spectroscopy, of course, by looking at different intensities emitted by these different lines. You can see on this right bottom corner, you have these ionized oxygen. So these numbers here indicate the ionization level of the atoms. You have Lyman alpha, helium-1, carbon-2, etc. So they all sample this region, the transition region, where the temperature is increasing from as low as 10,000 Kelvin to 1 million Kelvin, right? So what is exactly happening to the radiation? So you may have heard this saying that a photon from inside the center of the sun takes about 1 million years to random walk to the surface, right? So when you look at the sun, it does look like, you say it's a giant ball of fire or things like that. It does appear like a ball, a football. So you see a surface of that sun, right? But everything inside the sun is emitting. Why is it that you have that surface? You only see that surface, you don't see below that. So if this was a in-person, I would have probably stopped and asked this question. But let me just answer this here. So the reason that you don't see inside the photosphere, the visible surface of the sun, which is at 6,000 Kelvin, is because it becomes optically thick at that atmosphere. So basically you can see from these wiggly arrows here that these wiggly arrows are being scattered in all directions, right? So they are not coming straight to your eye from inside the sun. It's only at the photosphere that they start becoming straight enough. So the atmosphere becomes optically thin, which means the photons from that surface can now directly come to your eyes. So that's why you see that surface. Anything above that photosphere is transparent, which means they are in more technical terms, it is known as being optically thin. The atmosphere is optically thin or transparent to the visible light that is being emitted from the sun. And as you go out into the corona, you can see these wiggly arrows. They become more and more radially oriented, and they actually reach your eyes. So the first layer that we saw was the photosphere, and then comes the chromosphere and transition region, which is a very interesting part of the solar atmosphere. because in the chromosphere you have these jets known as spicules. So this is imaged in ultraviolet, extreme ultraviolet wavelength of 30.4 nanometers. So you see these jets going up and down, little jets here. These are spicules. And you will also have prominences, what are known as prominences or filaments. You can see the prominences in this region here, which are basically these giant loop, I won't say loop, but these giant structures hanging as if they are hanging in the atmosphere of the sun. So when the prominences, so this is on a limb of the sun, when the prominences are seen on the disk, they appear dark. This is in the same wavelength, H alpha, the H alpha wavelength, chromospheric H alpha wavelength. They appear dark in form of filaments. This image here, this black and white image here, is also an chromospheric H alpha image. And here you see a lot of structures here. You see what is known as the chromospheric network, the network and the internetwork regions. These grass-like things are again spicules that you see here. And in these internetwork regions, the magnetic field is predominantly vertical, whereas in the networks it is more horizontal. And then you have these plages and sunspots, for example, this region here. And flares, the eruptive phenomena of flares also take place in the chromosphere and transition region. So that is also what makes it really interesting. And there are a lot of satellite space-based instruments which look at this chromosphere and transition region in ultraviolet and extreme ultraviolet, because those wavelengths cannot be sampled from the Earth. Because UV is absorbed by the ozone. But there are other wavelengths like in infrared or reddish, for example, in H alpha, and which can be still sampled from the Earth. So this is the most interesting region.
Sorry, should I interrupt you with a quick question?
Yeah.
There is a question by Saurav Bhattacharya. The spicules extend up to how much distance?
Okay. So these spicules can go up to say from 6,000 kilometers above the photosphere to they can be as high as 20,000 kilometers above the photosphere. Or even so these are the ordinary spicules. Then there are what are known as jets or macrospicules that they can go, you can see sometimes these jets here in this movie, which are rising really high. They can probably go up to 60,000 kilometers above the photosphere. So I will talk about little bit on the theory or the physical mechanism behind the spicules later in my talk. So let's get to the next slide. And after that, after the chromosphere and the transition region, we have the solar corona. So this is the corona image during solar eclipse of 2009. And you would know by looking at this now, the photography enthusiasts would know that this is not a single image, but this has been built up by averaging over lots of images to reduce the noise. That's why you see these features, really clear features. And those images, those sequence of images are also not taken at the same time. I mean, they have been taken at a particular cadence. So they are not simultaneously taken images. So, but then if you average it, you get really nice and sharp, you see these features of the solar corona. There has been some image processing that has gone into this image, because if you look at this disk, this is the lunar disk, and you can also see the lunar what are these called, the features on the surface of the moon here. So it is a really it's a very processed image. And here you can see some features known as the Helmholtz streamers. And you can see that in the poles of the sun, the magnetic field is, more like a dipole. So probably the magnetic field is coming out of here and entering here. So one is the north, one is the south. It could be the other way. I don't know which is which right now by looking at this image. But there are really interesting features here.
Again, should I interrupt you with a couple?
Yeah, sure.
Yeah, there is a question by Mausami Jena. Why can't we see corona at normal times?
So I was going to come to it. So the white features that you see here is because of Thomson scattering. So the electrons in the corona are scattering the photospheric light towards you. So there are these electrons all around the plasma, mainly the ions and the electrons. So the electrons are scattering the photospheric light due to the Thomson scattering. You may have studied about Thomson scattering in your master's or bachelor's. I don't know which level you are in. So this Thomson scattering intensity is actually much less than what is emitted by the photosphere of the sun. So it's just the same reason that during the daytime you don't see stars, because the sun is really bright and the sky is scattering all this scattering all this blue light. The sky appears blue. So and the stars are really dim, so you don't see stars during the daytime. In the same way, the corona you can only see either during a total solar eclipse, or nowadays artificially you can see it by means of what is known as coronagraphs. So if time permits, I will show you some of the projects our institute is into related to coronagraphs, and I will also show some movies later on. So basically what happens in a coronagraph is artificially, so when the light enters the telescope aperture, so you put some kind of a disc in front of it, such that the disc has exact angular size as the angular size of the sun in the sky, so that most of the light from the solar disk does not enter the telescope. And that's how you can see these dimmer features as a result of the Thomson scattering. And this is the corona, which is said to be, the million Kelvin, at the million Kelvin temperature. So how do we study the sun? The different layers of the sun. So they are studied using different imaging at different wavelengths. For example, right now in the orbit around the Earth, we have the satellite known as the Solar Dynamics Observatory by NASA, which was launched by NASA in 2009, I think. But I may be wrong. Just check Wikipedia. I think 2008 or 9, and then it has been working since then. So the SDO observes the sun in different wavelengths. It observes the photosphere, and you may have seen magnetograms of the sun's of the photosphere. Rajguru may have already shown them. And apart from that, you can also view different layers. For example, the different layers, for example, the chromosphere, which is this layer here. And then you have these, for example, this blue layer is the transition region. And then blue and this red, they are corresponding to transition region. And then these are the much hotter wavelengths, which means that these at these wavelengths we are looking at a much hotter plasma in the sun's atmosphere. So if I show you this plot here, this is from the same instrument, known as the Atmospheric Imaging Assembly of the Solar Dynamics Observatory. So here I show the response function of the different filters at which the images were being taken as a function of the temperature. So here you see the wavelength in nanometer and the temperature, and what kind of wavelength it is sampling, and what position in the solar atmosphere. So you can see that here you have the chromosphere, the transition region, upper transition region, So 17.1 nanometer is upper transition region. So this 30.4 is already extreme ultraviolet. And then you have these hotter channels. For example, 19.3 nanometer images the solar corona at 1 million Kelvin. And then there is another filter at 13.1 nanometer, which images the corona at 10 million Kelvin, so which is like really hot. So you basically take the images of the sun. So each wavelength is sampling a different layer of the sun. So you don't ask the question that what is the height approximately, because when you are looking at an image, this image, the light in the image can be coming from different layers, not at a particular height. I can't say it is from, say, just 6,000 kilometer above the photosphere. It could be anywhere between 6,000 to 7,000 kilometer above the photosphere. But it is approximately sampling the layer of the sun. I mean, imagine the sun is like an onion with these different layers. And these are all sampling the atmosphere above the photosphere, right? So, and then that was one way. Spectroscopy is one way of studying the atmosphere of the sun, and the other way is using what are known as MHD waves. So basically the sun's atmosphere is full of a lot of structures. For example, they will have loops like this. You will have open flux tubes and regions above the active region, and so on and so forth. And analytically or theoretically, what people do is they assume that these loops are like what are known as flux tubes. So basically the idea is that inside these flux tubes, the plasma is frozen, what is known as frozen. So the plasma moves with these flux tubes. It's a totally mathematical construct, the concept of this flux tube. And then inside this flux tube, they will have certain conditions. So the plasma, when you say plasma, the different conditions of the plasma are characterized by its density, temperature, and the magnetic field inside the plasma. So basically the base conditions inside this flux tube. And the waves, different waves that propagate in these regions will carry information about the region through which they are propagating. So this is like helioseismology, but a little more difficult to perform, because you are now measuring an atmosphere which is really optically thin. So that has its own challenges. So this area of this technique, which is used widely in solar physics, is referred to as coronal seismology. So they use what is known as MHD wave theory to probe the structure of the solar corona. Basically, suppose you want to know that there's a nice bright loop. What is the magnetic field inside this loop? So you wait for this loop to oscillate, and then you measure the time period and wavelength, standing wave mode of this loop. And then from that you can estimate what are the base properties of the plasma inside these loops. So in a very, very simple way, I'm just trying to put it in a very simple way. So I'll go a little bit over the MHD, what do I mean by MHD waves and MHD equations. So please have faith that this won't be too tiring. I only have a couple of slides on this, but just to tickle your little gray cells. So these are the ideal set of ideal MHD equations. So the first one here is the mass conservation or the continuity equation. So for those of you who have taken a first course in fluid dynamics, you would have seen this equation already. And this equation is a variable, is an equation in, it solves for the variable rho, or the density of the plasma. So that's one variable here. The next equation is the velocity equation, or the Euler equation. So here you have basically the rate of change of velocity, and so basically this is the force, this is the acceleration balanced by the different forces. So this is again the Newton's second law then. So the first term is the Lorentz force, and then you have the gradient of pressure term, and then you have the gravity. And this equation is solving for 3 variables. So since this is a vector, the velocity is a vector, you have 3 components. So far you have 1 variable from the density and 3 from the velocity. And after that, the third equation corresponds to equation of an adiabat, or which says that the entropy is being conserved, for example. So P by rho gamma, gamma is the ratio of the specific heats, is 0. So this is the entropy or pressure equation, and this also contributes 1 variable. And then you have the Faraday's induction equation without resistivity, of course. That's why I call it the ideal MHD equations. There's no resistivity or dissipation anywhere. So then you have a total of 8 variables. So you have 1 plus 3 plus 1 plus 3. So the magnetic field is also 3 components. So you have 3 variables. But the good thing is that you also have a constraint on the magnetic field, which is the divergence of B is 0, no monopoles allowed. So that constraint reduces the number of variables by 1. So you will have 8 minus 1 variables now. And then what you do is you linearize your MHD equations. So the equations earlier were nonlinear equations because you were coupling the current and the magnetic field, for example. And here you had rho multiplying V. So these are nonlinear terms. So what you have to do is you have to linearize around a base state. So the base state is what it was existing, like a steady state or an equilibrium state. And the waves are perturbations over that. So essentially, we are doing a perturbation theory. So you have 8 MHD perturb variables, so which are this density, perturbation, pressure, the displacement. So the velocity I can convert to a displacement. And then you also have the perturbation in the magnetic field. So you have 8 variables here. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have 1 constraint. And there is 1 trivial entropy wave. So then you are left with 6 independent solutions of this MHD equations. So now you can do some mathematics, and then after linearizing these MHD equations, and arrive at what is known as the linearized MHD wave equation. And so this is an equation in this psi, which is the displacement vector for the wave. And then omega and k. So the omega is so these variables can be written as e raised to I k r minus omega t. So that is the usual wave equation. And so then you can write this equation in terms of a matrix equation like this, where A is a matrix multiplying this eigenvector, the displacement eigenvector psi equal to 0. And from your linear algebra, you would also know that these eigenvectors would have non-trivial solutions only when the determinant of this matrix is 0, right? So this matrix has terms which goes as omega square and k. And then when you try to find out the determinant of this matrix, you have a cubic equation is omega square. So you have omega 6, so which basically means that it will have 6 roots, 6 eigenvalues. So the 6 eigenvalues are these, say, the slow wave, the Alfvén wave, and the fast wave. And each has a plus and minus sign, which means that one wave is propagating along the wave vector k, and the other one is going in the negative direction, right? So these are the 6 roots. So that's how the MHD waves can be the number of MHD waves that can exist in this MHD system comes about mathematically from this this motivation here. These MHD waves. So one of the pioneers who proposed the existence of these MHD waves is Hans Alfvén, who was an electrical engineer from far north in Sweden, from Uppsala actually. So he was awarded the Nobel Prize in Physics for his work on Alfvén waves. So these MHD waves are then, I already told you about these roots, the 6 different roots. So 6 different routes are actually 3 for each for 2 different directions. So you have these slow waves, fast waves, and the Alfvén wave. So the slow wave, slow magnetoacoustic wave, it is known as the slow magnetoacoustic or magnetosonic wave, is a mainly longitudinal wave, just like sound waves. Sound waves are longitudinal waves, right? You all know that. So the slow mode is also mainly longitudinal, but it does have some transverse nature. And then the other mode of this MHD system of equations is the fast magnetosonic or magnetoacoustic wave. This is mainly transverse, but it can have some longitudinal features. So what has happened is, in the plasma, if you have magnetic field, you cannot have plasma without the magnetic field. So the presence of the magnetic field in the plasma changes the nature of the sound wave. The sound wave now basically is split into slow and fast mode, depending on how they interact with the magnetic field. Finally, you have what is known as the Alfvén wave. This is a new kind of wave. This is also known as the intermediate wave because its phase speed is in between slow and fast modes. And this is purely transverse. So these are the three modes that are in existence. So for example, here on the right-hand side, now you see a simulation of the solar atmosphere, plot of the solar atmosphere from our group. And here, this black line here is what is known as the plasma beta equal to 1 surface. Now the plasma beta is defined here, which is basically the ratio of the sound speed to the Alfvén speed, right? So because these can be very different in the solar plasma. In fact, in the solar corona, the Alfvén speed can be 100 times the speed of the sound. Right, whereas in the solar photosphere, it is exactly opposite. I mean, the Alfvén speed is, much less than the sound speed. So this plasma beta also has, like the temperature has a large gradient, the plasma beta also has a large gradient when you go from interior of the sun to the outside. So this black one is a plasma beta equal to 1 surface. So at this surface, the sound speed is equal to the Alfvén speed, the speed at which the Alfvén waves propagate. And then above this, you will have the slow mode. You will have this relation between the slow mode, the sound speed, Alfvén velocity, and the fast mode. Whereas below this beta equal to 1 surface, you will have a different relation. So the slow mode will always be slower than the slowest of the sound and the Alfvén speed, whereas the fast mode will always be larger than, a rough estimate is, larger than both the sound and the Alfvén speed, right? So let me now show you some examples of these waves. So the Alfvén waves, for example, let us look at some, how the Alfvén wave can be seen to be propagating. So you have these cylindrical tubes, well, imagine cylindrical tubes, not real cylindrical tubes, in the solar atmosphere. And then the Alfvén waves can be like a torsional wave. So you can see this propagating like a torsion. And they can be torsional Alfvén waves, and they can be what are known as shear Alfvén waves, which are basically what happens when you pluck the strings of violin, for example. So the strings undergo a transverse motion, and that's a transverse kind of a mode. So the Alfvén waves can be shear Alfvén, like the strings of a sitar or violin, or it can be torsional, like you see here. So they are doing this kind of a motion, if you can see my hands here. And the Alfvén velocity, which I was talking about for so long but didn't define, is given by is proportional to the magnetic field, the equilibrium magnetic field in the solar corona, divided by the square root of the density and the magnetic permeability. So this is the definition of the Alfvén speed in the corona. And these waves are incompressible. So when these waves are propagating, they don't cause any disturbance in density, which means that if you look at intensity of you are looking at intensity of light, you won't be able to see the Alfvén waves. You can only see Alfvén waves when you look at a Doppler map of the sun, of the solar atmosphere. So there are no intensity variations, nor there are loop shape or axis changes. So it's torsional, right? So the axis of this loop or this cylinder is never changing. And the phase speed is what is known as the Alfvén speed, and which is defined like this. Next, you have what is known as the slow magnetoacoustic wave, which is the slowest of the sound and the Alfvén wave. That is how you can remember it. So this is a predominantly longitudinal wave with maybe a slight transverse nature. So here you will have density variations along this cylinder. So like a longitudinal wave, and that you can see clearly as an intensity variation. So it is very easy to observe these slow magnetoacoustic waves. And this also, like just like the Alfvén wave, this also doesn't displace or distort the loops so much. And the speed is the slowest of the sound and the Alfvén speed here. Now next are the fast modes. So in 3D, the fast modes can be of two kinds. One is the sausage mode. The sausage mode is like the tube is it's called is changing this cross section along its length. So in this region, for example, the plasma is becoming compressed, and in this region it is becoming rarefied. So what it means is so the displacement is displacement of the magnetic field line, which is also transverse, right? I hope you are still with me, and you understand that this magnetic field displacement is transverse. But because of this, compression and rarefaction in the cross sections, there are density fluctuations. So that is giving rise to some amount of longitudinal nature to this wave. So this is not purely transverse, majorly transverse, but it has some longitudinal nature. And it is also fast. It is traveling at speeds higher than both the sound speed and the Alfvén speed in the medium. And this next mode is what are known as the kink mode. So in the kink mode, the loop or the cylinder is becoming distorted from its base value. So this oscillation is also a transverse oscillation. You can see that the displacement is perpendicular to the direction of propagation. Here, for example, direction of propagation is roughly along the magnetic field line, but the displacement is perpendicular to it. But still, it can give rise to density variations because of this distortion of this flux tube. Hence, this combination of transverse and longitudinal nature of this fast modes. And these fast modes, they are again. So this expression is basically for a plasma where the plasma beta is very small. So basically the sound speed is much smaller than the Alfvén speed. That has been the assumption here. And so, it is given as a combination of the Alfvén speed inside the tube and outside the tube. So this comes about mathematically again by linearizing or MHD equation for this kind of geometry. Okay, so now let us come to the importance of magnetoacoustic waves in the solar atmosphere. So before I go over this, are there any questions on what I spoke so far? No? Okay, so...
There are no questions.
Okay. So, because I won't be able to see...
Yeah, there was earlier question regarding the PQs, so I just waited till the end. So what causes these PQs?
Yeah, right time to ask the question.
Yeah.
So let me just motivate it using some observations. So this is again a movie from the Hinode Solar Optical Telescope, which is a Japanese instrument which looks at the solar, which is looking at the solar limb near the poles actually. So you can see these jets. Often it looks like swaying grass-like structures, and these are like 10 to 20 megameters long and 300 to 500 kilometers thick. And you can see these are swaying, and you can see the bunches rotating here. So these spicules are what we believe are caused by the slow magnetoacoustic waves. So here is again a chromospheric alpha image of this, the same thing, but in H alpha. So this can be taken, this is from the ground, and so this one is from the ground, this one is from the space. So, and this is on the solar disk, of course, the right panel is on the solar disk, whereas this is on the solar limb. So on the solar limb, you can see this clear, really nice, even though this is from space, you can clearly see this nice, rotating and swaying properties of this solar spicules, right? So what we did recently in our group was, this is a computer simulation. So what we did was we took a solar-like atmosphere, and then we subjected it to some vibrations, some quasi-periodic vibrations. You can see the nature of these vibrations. So this is the time, if you can see my cursor, versus the vertical velocity. So this is the forcing that we apply at the photosphere of the model. And when we apply this forcing, we see that there are these plasma jet-like features which is being formed, and it makes these constant excursions into the much hotter corona. So we believe this, what we see here are spicules, synthetic spicules. And you can see two properties here that you also saw in the observation. One is the spicules are being formed here, and they are because of these slow magnetoacoustic waves, which are also propagating at the same speed as the speed of these jets. So the speed and lifetime of these jets are similar to the speed of the slow magnetoacoustic wave expected in this low solar atmosphere. And apart from that, you will also, if you see this plot, the right hand contour plot, which shows the temperature, the logarithmic temperature in the domain. So this is the vertical axis and this is the horizontal axis of the domain. You would also see that you see some waves which are propagating in this fashion, transverse fashion, which causes this swaying of these spicules. So those are what are known as the fast kink waves here. So, so this is a 2D model, so you cannot have Alfvén waves here because Alfvén wave requires the torsion and the twist. So in a 2D model, we cannot have the Alfvén waves, but we can have both the slow and the fast magnetoacoustic waves here. And what we believe is if the solar photosphere experiences this kind of vibration, acoustic vibrations. You may have heard about P modes from Rajguru's lecture. P modes, which are excited because of the convection. So these P modes can become steeper and steeper as they propagate into the solar atmosphere. So it's just like tsunami. So what happens is in tsunami is that when the tsunami is initially born somewhere in the deep waters, the amplitude is not so much, right? So as it propagates towards the beach, the shallower and shallower water, the amplitude of the tsunami increases, right? It becomes steeper and steeper. So in the same way, these nice, quasi-periodic vibration, they become steeper and steeper, and they break into shock waves, and they form what are known as magnetoacoustic shocks. So that is what is giving rise to this solar spicules. And then here is another simulation from our group. So here on the left-hand side, this is again the same movie I showed earlier from Hinode Esoti, where you see these spicules, but now the simulation instead of in 2D has been done in 3D. And we, instead of these quasi-periodic forcing, we have used a solar-like convection. So here you can, compare, if you look at this yellow rectangle here, so the simulation corresponds to a rectangle of a similar size like this. So you can see that you can see these rotating bunches of spicules, rotating and swaying bunches of spicules, which you also see in these 3D simulations. So these are again, these swaying things are again because of these fast magnetoacoustic waves. I won't here focus on what is causing the rotation, because that has a totally different reason. So right now I will only focus on what is happening because of the MHD waves that are leaking into the solar atmosphere from the photosphere.
Would you like to take a couple of questions?
Yeah, sure.
So there is a question from Vignesh Vishwanath. He is asking, in which part of the spectrum or MHD waves are observed? So he just wants the...
Oh, okay. Yeah. So these waves can actually be observed in different parts of the spectrum. So I will come to... Yeah. So for example, these spicules are being observed in calcium 2H, which is again ultraviolet, and again this H alpha, which is the red part of the wavelength. So in a variety of wavelengths, from the visible to ultraviolet to extreme ultraviolet, these waves can be observed. So depending on which region of the sun you want to study, you will use that particular wavelength. So for example, H alpha, we sample the chromosphere, and so will this calcium 2H. So depending on the region of the sun you choose, you will have to choose your wavelengths accordingly. The lines that you observe in those regions have to be sampled. So you can observe it actually in a variety of wavelengths, from visible to ultraviolet to extreme ultraviolet, and also in X-rays actually, like I'm going to show you later. So okay, so this was about, so far,
there is another question.
Yeah. Okay.
Yeah, whether these, how this MHD waves causes the ejections like prominences, jets and all.
Oh, so the MHD waves are not the only reason behind the prominences and jets. Okay, so for jets, I showed you this movie already. That what is happening is the waves are like a tsunami, so it is becoming steeper and steeper, and then as it goes upwards into the atmosphere, the fronts become steeper and steeper, and as they propagate, they energize the plasma along the way. So as they travel up, they also keep on energizing the plasma, which then forms jets. Right? So it is just like what happens in a tsunami. There's steepening of wave fronts, or shock, and turning into shocks. So that is what is causing these jets. But prominences have a different reason. They are not caused by these MHD waves, right? So one thing that I should mention here is that so far we have been looking at regions of the sun where the magnetic field is vertical, predominantly vertical. So you see these jets, they are vertical and open. Right. So now we will go over to cases where this magnetic field is like loops. So it's not that all the regions, like the open magnetic fields can be found in, for example, coronal holes, and mainly near the coronal holes and above active regions, for example. However, in the quiet sun, the magnetic field will be more like loops, will be closing. So there will be a loop coming out of the photosphere and then again going back to the photosphere in form of loops. So now we will focus on those. So even those can be studied as a diagnostic for the plasma properties in the atmosphere. So typically, this is a cartoon of a typical loop that is considered by theoretical solar physicists to calculate the dispersion relation for these fast kink waves. So again, they assume that this is a loop, And here, this funnel kind of a thing is actually in the chromosphere. And then as it goes into the transition region in corona, these loops, they expand because the density and the pressure is really low. So it cannot be confined to a narrow region, so it expands. And then this loop can, fall back on itself to another part of the and have its foot point at another part of the sun. So there can be loops like this. And these loops will have some properties in the sense that inside the density, magnetic field, and temperature will be different from what is outside. So this can be these base states, what are known as base states in linear MHD wave theory, can be used to use as a diagnostics for the magnetic field, for example. So here is a movie taken by, again, SDO, two different wavelengths here. And then you can see that there was a flare somewhere here. And if you look at this loop, if you look at my mouse carefully, you will see that this loop is bouncing back and forth, right? So this movie is also playing in a loop. So you just look at the loop and it is bouncing back and forth. So that is also a loop kink wave, the fast mode. These were first discovered by the TRACE satellite way back in 98. And they have a very wide variation in the time period. And sometimes these waves are damped, which means that this loop doesn't keep on vibrating for a long time, but it stops after some time. And the displacement is typically 1,000 to 10,000 kilometers. So megameter is 1,000 kilometer. So these can be, these oscillations can be way to understand the properties of the plasma and the magnetic field in this region here, right? Okay, so this was about the MHD waves, and usually the quiet sun. Only a small part of it. Of course, the sun is much more dynamic, and I'm sorry I cannot cover all of it. So I just gave you a small snippet of that. So now we will go over to what is known as eruptive or more energetic phenomena. So before that, if anybody has any question, I will be happy to answer about what I have already spoken about before.
Yeah, there is a question by Ashutosh Yadav. He is saying why the coronal loops vibrate.
So these coronal loops are actually vibrating. Okay, so there was a flare. Let me run this movie again. So we'll see that there was a flare, and the flare basically disturbed the system. And then that led to, these loops were, just standing there and minding their own business. But these flares disturbed the plasma near these loops. And that is what made these loops vibrate. But they don't keep on vibrating forever because of inertia, not the mass inertia, but different reasons like damping. And then because of the damping, the vibration will stop after some time. But usually when there is a flare nearby, you often see that the region around these loops is disturbed, and that causes the vibration of those loops. Is there any other question?
There is another question by Gautam Shankar. He's asking, do flares interact with each other?
You mean one flare interacting with another flare?
Yeah, probably.
Okay.
That's successive flares or homologous flares. That's homologous.
What you mean. Yeah, I was going to say that. Vasant, you would also know about that. That yes, we indeed have what are known as homologous flares, but they are not simultaneous flares. So sometimes, if there is a flare that can, so I'll let you know by and by, what causes flares. But there may be what are known as sympathetic flares and homologous flares. I don't have slides for that. But what sympathetic flares means that suppose there's a flare in one part of the sun, and that flare has disturbed the region, the magnetic field configuration, in such a way that a region slightly far away from it has also become unstable. and that also flares after some time. So one flare can, can be a last straw on the camel's back, the proverbial last straw on the camel's back for the next flare. Similarly, there can be what are known as homologous flares. Homologous flares are those that take place in the same region of the sun, in contrast to the sympathetic flares. And there also, one flare, ejection of one flare can again cause another flare. So but not always. I mean the answer to this question is not very simple, but a more simple answer is that there are these sympathetic flares where you can have one flare which is a cause of another flare, but that is a sort of cause and effect interaction that the flares might have with each other. Yeah, so Vasant, are there any more questions?
Yeah, please go ahead.
Okay, so I see that I have 20 minutes, so let me see how much I can cover. So the eruptive phenomena in the solar atmosphere, which mainly take place in this chromosphere transition region and the corona, are categorized into roughly two parts. One is the solar flares and the other one is the coronal mass ejections. You might have read about these in the news, and then I think sometime few days ago there was this news about solar cycle 25 giving rise to its first X-class flare. So these solar flares and coronal mass ejections are related to each other, but again, it is a little bit complicated. They are two different things, and I'll try to keep them separate, one from the other. So these solar flares are basically rapid and intense change in brightness. They last for 5 to 20 minutes. And they are caused by this sudden release of magnetic energy that is built up in the solar atmosphere. And the energy released is of this order. So that's like really huge. You can compare them with the nuclear bombs we have. But then these energies are much smaller than the amount of energy the sun is releasing from the photosphere. But during the flare, so they release huge amount of these energies, and the temperatures, again, these are not the Planck black body temperatures. The kinetic temperatures can reach as high as 10 to 20 million Kelvin, and they can end up emitting extreme ultraviolet rays, UV, X-rays, and even gamma rays. So in a flare, you see the energy emitted in the whole spectrum of the whole electromagnetic spectrum, starting from radio, microwave, optical, UV, X-ray, gamma rays, everything. These flares mainly originates in active region or sunspots. So those are the most interesting regions. So if you didn't have sunspots, the sun would be quite boring. So most of the eruptive phenomena, they take place above the active regions. And the frequency of occurrence is modulated by the 11-year sunspot cycle or the 22-year the dynamo cycle, which you may have already learned about, right? So how are X-ray fluxes measured? So they are measured by these geostationary satellites, which belong to this US Air Force. And then there used to be many ghost satellites, I think 25 or something, out of which maybe 18 or 11 are operational. I don't remember what, but what they do is they measure the X-ray flux that is coming from the sun. And then they tabulate this X-ray flux. So this is watt per meter square versus time. And then they measure this X-ray flux in two different bands. So one band, which is indicated in blue, is this 0.5 to 4 angstrom. And the next one is this red band, which is slightly harder than the bluer ones, in 1 to 8 angstrom, a broader band. So here, so what happens that if you, so this is, they are looking just at the sun as a star, and they are measuring how much of flux they are receiving, X-ray flux they are receiving. And then, so they have these measures these curves here, light curves for the X-rays, and then they draw these logarithmic scales here, and each decade in the log scale is denoted by these letters A, B, C, M, and X. So historically, actually, C stands for common flare. So the C class flare is the most commonly observed flares on the sun, whereas B and A are smaller, weaker than the C class, the common class. M stands for medium class, and X-ray is extreme. So X-ray, X class. So when a flare you see is X class, it means they are the strongest of the flares that we see on the sun. And further, in some cases, you see X2, M5, X6. So for example, in this decade, so it corresponds to this, 2, 3, 4, 5, 6. So this, linear scale here. So it's logarithmic, and then again, each decade is divided into nine points here. So the 6 means the power here is 6 into 10 raised to minus 4 watt per meter square. That's what X6 means. Similarly, M5 would mean that it is M class, and it is 5 into 10 raised to minus 5 watt per meter square. So that's how the flares from the sun are measured by these ghost satellites. But these solar flares can also be observed in a variety of other wavelengths. So here, this is a movie from NASA's SDO satellite again. So the SDO satellite is a very most useful satellite that we have, because it is looking at the sun with different eyes, right, at different wavelengths. So a single flare can look different in different wavelengths, which means that in the same flare, you have plasma at different temperatures. And the study of these, this multiple wavelength thing, this multi-thermal structure of the plasma is also very interesting of what is exactly happening in the flare. It will tell you about the morphology of, the flare, starting from where the flare originated to how much energy it released, where were the gamma ray particles released, where were the high energy particles released. It will give you the information of all that. Right, so the flare looks different in different wavelengths, and if you study all these wavelengths, you will get a comprehensive view of the solar flares. Now, these solar flares occur mainly because of what is known as magnetic reconnection. So you see this cartoon here on the right. So what is happening here is there was a magnetic flux tube here, and because of some reason it became destabilized, and then there was a magnetic reconnection in this region here. So what was happening in this region is shown in a very simple cartoon here. So you have this red magnetic field line and the blue one, they come together and then they reconnect. So initially the red and the blue magnetic field line are oppositely directed. Now you know that the magnetic field is a physical quantity. So you cannot have at any point in space, you cannot have magnetic field pointing at two different directions, right? So it cannot be multi-valued, it has to have a single value. So in the reconnection region, that property is violated. So it tends to have multiple values, but that is not allowed in nature, right? Because in nature, you have what is known as resistivity. So because of this resistivity, what happens? It's as if the magnetic field was spliced using a scissor and then reconnected. Now this splicing of the magnetic field and reconnection releases energy. Releases energy in form of electromagnetic, non-thermal, X-ray, high energy particles and everything. And that is what you see in the flares. So here is again a cartoon of, solar prominence here. And then you have these magnetic field lines and they are reconnecting. And then you have just below the reconnection, you have what are known as the hot post-flare loops. So the word flare, when you hear the word flare, you should think that there is some reconnection going on somewhere in that region. So below that region, the magnetic fields have reconnected already. So these are known as post-flare loops, and they are really hot because of the energy release at the loop tops here. Right. Now, so these flares, where do these flares take place actually? So these flares basically take place in certain regions known as sunspots, over regions which are known as sunspots. But not all sunspots are super active. There are some certain spots which are known as the delta sunspots, which are less than 25% of all sunspots that appear during a given solar cycle. Yet, most of the X-class, X-ray producing flares take place above the delta sunspots. Now, these delta sunspots are super active, which means they flare repeatedly. So they can generate what is known as homologous flares. And when there is an active region which is giving out flare after flare, multiple flares, they can be highly geoeffective. So some of them, can during the disk passage of the active region, it is probable that if it is constantly ejecting ejecting these flares, some of them might be earth directed, so they can be highly geoeffective. So here you see this photospheric G band intensity of active region, and please focus on this active region here. And here you see that there is a penumbra, and inside the penumbra there are two umbras. Like, this is highly unusual. Usually, sunspots would have one penumbra, and inside it they will have one umbra. There's one umbra surrounded by one penumbra, whereas here they have two umbras inside one common penumbra. So that those regions are what are known as delta sunspots. Now here is the vertical magnetic field, the magnetogram of such a delta sunspot, not the same delta sunspot, a different one. And you see that these are the two umbras here, the black and the white. So the black corresponds to magnetic field going inside the photosphere, and the white is what is coming out of the photosphere. So these have been measured using the Zeeman splitting, the way the magnetograms are measured. And you see that inside these twin umbras, the magnetic field is actually opposite, which means that the magnetic field can be highly stressed in these regions. And easier way to understand is that the more stressed or twisted the magnetic field is, it's more likely to store more energy. So they can emit more energetic flares. Right. So some time back, we also proposed a model for why such delta sunspots can flare repeatedly. So we made this very simple model, but it was of course a 3D MHD simulation. But then we had these very simple initial conditions, out of which we formed this delta sunspot. You can see on this right here. So the blue and the yellow are the different signs of the vertical magnetic field. And you can see there are these two small spots which are colliding with each other. And after colliding, they stick to each other like, a delta sunspot. And then this delta sunspot, since it has a lot of shear, that can give rise to multiple eruptions. So that is what I also show here. So what we did was we started with a very simple initial condition, basically horizontal magnetic sheet, and that magnetic sheet, because of buoyancy instabilities, it got warped and it formed magnetic tubes. And when these tubes rose to so this magnetic sheet is in the subsurface below the photosphere of the sun, and because of buoyancy, it tried to stick its neck out of the photosphere. So here, this orange thing is basically the granules, the convective granules of the photosphere. And it tried to stick its neck out. And when it tried to do so, there were these vigorous, highly energetic reconnections that took place. So these tubes are magnetic field lines colored by the vertical velocity. So you can see these jets, the reconnection jets appearing here. So we proposed a very back of the envelope model about to explain why such delta sunspots can flare repeatedly. So this is again this collage of the flare, the same flare observed by different wavelengths at SDO, and you do see different features that is occurring at each different wavelength, because you are sampling the plasma at different temperatures. So you will get a very holistic view of the entire region where the solar flare is occurring. And this is again from another simulation where we found the multi-thermal structure of that eruption region that you see in SDO. I showed you this multi-thermal this multi-thermal structure. So you see that here also. So in this movie, you see that there are these red hot post-flare loops with a very high temperature. And this region, this sky blue region, which you see rotating, is where the reconnection is taking place. And then you have these cooler regions called the filament, that's the erupting filament or the prominence material. So which is erupting, and that is the coolest part. So you have all sorts of temperatures in this kind of a multi-thermal region of the model. So now let me go over to CMEs. So what I could do is I only have 5 minutes left till, so I can cover this in the tutorial part, and I can stop and I can take some questions about what I have done.
Yeah, okay. So there is a question by Aditya Suresh. So what causes the reconfiguration rather than just tangled magnetic fields? How they perfectly recombine like in that cartoon?
So that cartoon was quite perfect. It's true, because it is a cartoon. So to make this clear, it is like, since it is a cartoon, to make you visualize what magnetic reconnection is, it has been drawn in a very simple manner. Whereas if you see the simulation here that I showed, so these field lines here, those are also reconnecting, and you see that they are much more tangled. So you see there are flux ropes which are being formed and then ejected here. So these here also there is this current sheet. You can see a very complicated structure of this, the magnetic field line here as well, where it is what you mentioned as tangled. So you see those tangling here as well. But because they are tangled, so oppositely directed field lines can come really close together. You also see it here. So in this current sheet here, so you can see this really light blue current sheet. That is where all these tangled field lines, oppositely directed tangled field lines, are coming together. And it is not as simple as that cartoon that you saw. So you are right, they are tangled, and because of more tangled they are, more likely are oppositely directed field lines likely to come close to each other and reconnect. Because as I said that the magnetic field cannot have two values, cannot have multiple values at any point. Mathematically, that is not allowed.
Yeah, there is another question by Samantha Ruth. She's asking, can solar flares disrupt communication via satellites, and also how do they interact with Earth's magnetic field? But it is a bit off topic.
It is not an off topic, because I'll probably cover that in the CME part. So you are right, they do affect the Earth's. So Earth also has a magnetic field. So you may have heard about ionosphere, magnetosphere, different layers of the Earth's atmosphere, and then they induce currents in those regions. So flares are basically energetic particles, right? And then they can travel via the magnetic field lines that connect the sun's magnetic field to, they come and reconnect all the way to the Earth's magnetic field. So I will show you some movies hopefully, where I can motivate that that is how it is, that is how auroras are formed and communication is disrupted and all that. So please, if you wait till the next part of the talk, I think it will become clear.
Okay, there are a couple of questions from YouTube chat box. Okay, or there is a question from Aswati K.
Hmm.
Are prominences also eruptive like flares? How do we differentiate them?
So these prominences are basically part of these part of these so there are these magnetic flux tubes, right? So this dark blue dots here is what is the prominence material. So this prominence or the filament material basically lie so when the flux tube or the flux rope that is formed in the corona is not doing anything, it is just lying quiescent before eruption. So the filament material is just like a lazy person lying in a hammock. The hammock is made by the magnetic field lines of the flux rope. So the filament material is heavy, it is cold. So you can observe it in chromospheric lines. It's much colder than the reconnection regions, for example, or the flux rope itself. So they just lie quiescently, lazily in the hammock. Now, when during a flare, the flux tube itself, or the flux rope, let me call it a flux rope, erupts. With it, the filament is also forced to erupt, right? So in a way, this filament is part of this multithermal structure of the magnetic flux rope. So the magnetic flux rope holds the filament in the dips, like a hammock holds a lazy person. So visualize it in that sense.
Okay, there is another question by Raymond Goyal. What causes the damping in oscillations of the loops?
That's a good question. So, okay. So, what causes there can be different things. So when I showed you the MHD equations, I said that there are no dissipation parameters in that. But however, nature is not like that, right? So you have viscosity, you have resistivity, you have thermal conductivity, and you have all these kinds of ways in which the energy flux can flow from one region to another or dissipate. Like resistivity is what is causing these magnetic reconnection. So when you linearize your MHD equation in presence of dissipation parameters, which I have not shown you here, but people have done, then you get some damping parameters. So I showed you this equation, right? E raised to I kx minus omega t. So whenever omega is real, then you have a wave, right? However, when this omega has an imaginary part and which is negative, you will have damping, right? And that damping maybe is because of these thermal conductivity and this magnetic resistivity, viscosity, all these kind of dissipation parameters which are present in the solar atmosphere. I mean, this is a very simplistic answer. There are more complicated things, more complicated physics of that, but just imagine that it is because of these dissipation parameters which are present that leads to this damping.
Okay, there is another question by Mausami Jina. So why different types of spectrum are used to observe solar flares? So probably she meant why different wavelengths probably.
Yeah, so these different wavelengths correspond to different temperatures. So if I go back to this initial slide that I started with, I think yeah, this slide here. So you see that here each wavelength is sampling a particular temperature. So for example, look at this 171 angstrom wavelength, 171 angstrom or 17.1 nanometer. So this is sampling a temperature which is around 80,000 Kelvin. Whereas if you go to some other wavelength, say this 131, 131 is sampling two different temperatures. One is at a lower temperature, say around 500,000, and the other one is at 10 million Kelvin. So different wavelengths are sampling different plasma at different temperatures. So that is why if you want to look at the multithermal structure, I mean, it's not in a particular region, the plasma is not at constant temperature. Different regions have different temperatures, and if you want to study that, you need to look at different wavelengths which will sample those particular temperatures. So here I have given this table, and you can also get it by searching on the Google. So just look at plasma properties using AIA HDO satellite. These are filter functions of that AIA assembly of AIA instrument of the HDO. So that is why we have to use different wavelengths, because they'll sample different properties of the plasma.
Yeah. Means I don't see any more questions. We are already into the tea break.
Yeah. So then let's go for a break, and then I think when we come back, there's Rajguru's tutorial, and then in half an hour I will try to cover some space weather where I left some open-ended questions.
Okay, sure. So let's break for a tea, and then we will be back at 4:10.
Okay.
And the attendance will be open. Attendance sheet will be open till 4:10. Okay. So please, if you haven't done it, please sign it. Thank you.
So just one point. I think everybody must have got the tutorial material that I emailed or shared on the chat box. So you can open and maybe read the instructions there. There is a README file which you can read.
Hello. Hi, Crispin, or the host.
Yes.
Okay, can you make me co-host? I'm not able to share.
Okay, yeah. Yeah, it's done.
Okay, okay. Hi, everyone. Think those. Crispin, you can not, you don't have to record right away. I'm just trying to
Yeah,
explain.
okay.
When I tell you, you can probably start. So for those of you who are accessing the Google Drive, I have put the README file. There is a README file which I am showing right now. It is an ASCII text file. So I don't know, whatever, you can download it and read it in your notepad or some kind of ASCII readable software, you know. Okay, I hope that helps. So if you just double click, it may not open in Google. It is an ASCII text file. You have to use it, open it using a notepad or something, which is what I'm showing. The README file is what is shown on your screen right now. It just explains what to do with the different files. And then you will see. Okay, probably let me wait, let everybody join, and then we can. I will explain this. So I don't know who is Vasantaraju. Are you the host? I mean, are you the moderator now?
Yeah, the Manoj is supposed to moderate this session. Okay, yeah, just wait for a couple of minutes. I will.
Okay. So let me know when I should start.
Yeah, sure. Okay. Okay, I don't see Manoj in the list. Okay. So how are you going to divide this session? Means first hour you are going to speak, and then later Piyali Chatterjee going to speak, or how it is?
So what is the total time for this session?
This is 14:10 to 1. Just a minute.
Rajguru is for 1 hour.
Totally 1 hour?
Yes.
Okay, so let me try to finish within 30 minutes then.
Yeah, it is 1 hour. So it is 4:10 to 5:10. So half an hour you can go ahead and
Okay,
will be
sure.
handled by the PM.
All right, I will try to finish in half an hour. Maybe 5 minutes here and there, but I hope it's okay. All right, okay, let me.
Okay, there are 193 participants. So you please share your screen and then.
Okay, let me share. I think I will share the whole desktop. So I'll be.
Yeah.
You see my whole desktop?
Yes, we can see.
Okay, so what I have opened is this Google Drive. I hope everyone can see. This is the Google Drive I put in. There is a README file. Okay, so if you double click that, it won't open in the browser. So I have opened it separately. I hope you see this Google README file. I hope everyone can see it.
Yes, we can see that.
Okay, so all the students, you can just read this README file. I explained certain files here. There is a data file called jcd model s.data.dat. It is an ASCII file. I don't know. It has 10 columns, 2,482 rows. I hope we can read them. Okay, I will come back to it, how you will use it. So we are not going to do it within half an hour. It is not possible. So I'm just explaining to you the problems you will do. Probably you can do it later at your leisure as a kind of a homework. Okay, so there is a model file. This is the sun's model of the sun in 10 columns, and the 10 coordinate, the 10 variables are written here. The first column is the real coordinate, density, pressure, temperature, adiabatic index gamma, acceleration due to gravity g, and then sound speed c, Brunt voice-over frequency divided by g, and then acoustic cutoff frequency. Okay, I will explain to you. I mean, I have given certain equations which have this parameters. And then there are these FITS files. There are really large FITS files. So those are images of the sun, a small region on the sun in Doppler. Okay, so the tract V, capital V at the end of that tract stands for velocity. Scale is actually 0.06 degree per pixel on the sun in heliographic coordinates. Okay, I will tell you, what the size of a heliographic degree is. So it's a 3D, it's a data cube, a series of images, X in X and Y and time. That's the dimension, 500 by 12, 500 by 12, and 1121 time instance. So it's a 3D data cube. I will again explain to you what you want to do with that. Okay. All right. So that is the thing I wanted to. So before actually going and doing this, what I am going to show in the slides, let me now show you. Before actually doing this, you see my presentation now. Okay, I hope you see it. This is what we discussed in the morning. Okay, so let us do a very simple problem. So someone in the morning asked the question. Okay, when in the beginning I told you in the vital statistics here, I told you the central temperature is 15.7 million degree Kelvin, right? Someone asked, how do we know the temperature is this much? Okay, so you can determine that in a very simple way. So I started with off with these equations. I told you the very fundamental equation we use is the gas pressure is balanced by, it balances the gravity force. So dP by dr, the change of pressure as a function of distance through the radius of the star, gas pressure gradient, is equal to rho times the g, the acceleration due to gravity. Okay, so this is some handwritten notes on that. So you can convert that equation, dP by dr is minus rho g, in terms of mass coordinate. Okay, so you will end up in an equation like this, dP by dm. So mass coordinate is dm by, so you basically dP by dr is minus gm by rho square, by r squared rho, right? So you multiply by dm by dr. Dm by dr is, it comes from the mass conservation equations. So this capital is the same m as the small m I use here. Okay, dm by dr is 4 pi r squared rho. Okay, this is from the mass conservation. So you combine that in this, you will end up in an equation, dP by dm is minus capital G, this is the gravitational constant, mass divided by 4 pi r power 4. Okay, so I would ask you to use this equation to determine the central, let us say, central pressure. Okay, I have done this here, so you can do it yourself. Just assume in a kind of a order of magnitude estimate. So dP by dm is minus gm by 4 pi r squared. So you left hand side, you just assume that dP is just the pressure at the surface minus the pressure at the center divided by the whole mass for the whole sun as it is applied. Then it will be left hand side is minus central pressure divided by the total mass of the sun. The right hand side is similarly, you can replace the small m by the total mass of the sun and the radius by the total radius of the sun, and then you work out this. So you will get the central pressure. Okay, so you can numerically estimate given the mass of the sun. So I told in the vital statistics, I told you the mass of the sun is 2 into 10 power 30 kilogram. All right, so the radius is 6.96 into 10 power 5 kilometers. So you can either, whatever units you want to choose, you can do it either in CGS units, centimeter gram, or kilogram meter. You have to convert it into meter. So these numbers, and you estimate the central pressure. Okay, and then assume an equation of state P equals R rho T. Okay, I am not showing it here. You all know the ideal gas equation of state. Let me see if I have it here. So here, P is R rho T by mu. Okay, if you know the central pressure, you use density, central density, and central temperature on this. Okay, and then using this expression, what I have here for the central pressure, you can just simply estimate temperature, central temperature. Okay, so this is one exercise you can do. Anyway, I mean, I hope maybe you can do it as a homework. I don't know when I can check this, but we will find a way to check this. All right. Okay. So that is there any question here?
No, not yet. There are no questions. Yes.
Okay. So I hope they understood the question. So actually, in the morning we discussed, someone asked, how do we know the central temperature is of the order of million degree Kelvin? Okay. So the basic principle we use, we assumed when we discussed how we build a model of the sun using stellar structure equation, which I described, we basically assumed that the gas pressure, balances the force due to gravity. Using this simple fundamental principle, you can approximately estimate the central pressure and temperature. I showed you how to estimate the central pressure using the force balance equation. And then you combined it with the ideal gas equation of state. and estimate the central temperature. Let us see what value you get. I hope you can do that. Okay, so that's one thing I thought of asking you to do. And then we discussed, okay, so another simple exercise I thought of asking you to do is, so we discussed, for example, let me play this. I told you one of the basic inputs we use is among the three inputs which I have shown here in this slide. The second one is, it comes from nuclear physics, nucleosynthesis, how protons collide and in the core of the sun, how they fuse and produce helium. There are a set of reactions. You don't have to worry about the details. But I wanted to explain to you the basic principle behind how much energy is produced due to nuclear reactions. So basically, you all know this. I have put my handwritten notes as part of the course. So suppose if J nuclei of mass Mj fuse to produce a final nucleus M, My. So the mass difference, okay, it is called the mass defect. If you sum the mass of this nuclei which are fusing, and then you take the resultant nuclei, which is My, you take the mass difference. If you call that as delta M, that is a mass defect. Okay, so the famous formula which relates mass and energy is this Einstein's formula, E equals mc squared, which I'm sure you all might have come across or studied. So that is the formula we need to use. So let us assume that hydrogen is fusing into helium. What is the mass of one hydrogen? Basically, it's a one proton mass. It is 1.0079 atomic mass unit. One atomic mass unit, the mass is, it's given there. I hope you can read this. 1.6605 into 10 power minus 27 kilogram. Okay, that's the mass of, that is the one atomic mass unit. One hydrogen nucleus or the proton mass is 1.0079 atomic mass unit. Okay, and four protons combine to form a helium. Okay, and the masses are given, 4 hydrogen masses and helium 4. 4 hydrogen atoms or 4 hydrogen nuclei fuse to produce one helium. Okay, so the mass difference is 0.029 into 1 atomic mass unit. Okay, so basically it's about 0.7% of 4 times the mass of the protons, the hydrogen nuclei. 0.7% of that is lost in energy, which will go into delta M. That delta M is 0.7% of those 4 hydrogen nuclei mass into C squared. Okay, given this information, okay, I give you the luminosity of the sun, okay, which is, which is given here on the right side, 3.86 into 10 power 26 watts. Okay, so you determine using this, it's a very simple, straightforward numerics. How much mass is lost per second due to nuclear fusion inside the sun? Okay, you determine that. Given this luminosity is how much of energy, total energy coming out per second. What is joules per second? Okay, so it's 3.86 into 10 power 26. How much mass is lost? Okay, if this is it's very simple. Can anyone tell me quickly if they can do this? Okay, anyway, you can do that exercise. Let me give you this. Has anybody found the answer for this? If this much of energy, joules per second, is going out, okay, it's a simple equation to use is E, energy is mc squared, So I asked you how much mass is lost per second due to nuclear fusion reactions, given this luminosity. Okay.
If somebody has an answer, you can unmute yourself and speak.
Right. Okay, I am showing that.
There is a answer by Gautam Shankar, PK,
okay.
And he is saying it turns out to be 4.2 into 10 power 7 kg per second.
Right. The answer is here on your screen. 4.26 into 10 power 12 gram per second. That's what I get. He said 10 power 7 kilogram
per second.
It should be 10 power 9, right?
Yes.
Okay, anyway, so the way to do this.
So 4.28 into 10 to the power 9.
Correct. That's correct. Okay. All right, good. So it's just a simple thing. Okay, so you basically understand how energy is generated, so basically hydrogen fusion to helium, there is a mass defect that much of mass is converted into energy. And that is what the sun is shining through. So that is what is given here. Okay, and now a related problem. Okay, it is you can read that at the next to that. Again, I'll put to full screen. So the total mass of the sun, anyway, I given you in a vital statistics, it's about 10 power 33 grams. It's actually 2 into 10 power 33. Now estimate the lifetime of the sun. Okay, by lifetime you mean how long the nuclear fusion can happen inside the sun. Okay, assuming that only hydrogen is fusing. So assuming basically sun is fully hydrogen, 100% hydrogen, and that only 10% of its mass converts to helium. Okay, once 10% of hydrogen is converted, it's assumed that it is sun's life ends. Okay, so estimate how long it will live, sun. Okay, again, a simple application of what we just discussed. Okay, someone can do that quickly. Can give me the answer. Okay, so this is the total mass. 100% of the mass is hydrogen. Only about 10% of it is converted to helium. And if that is the one which determines the lifetime of the sun, so how long it will live. So here we determined how much per second. This is a related question. How long it will take for the sun to use 10% of its mass. Anyway. Anyone has an answer? Order of magnitude estimate? Okay, I don't know, I don't see. All right, okay, you can do that. It's called the nuclear time scale of the sun. Okay, it is also approximately equal to the age of the sun. You all know, I told you currently sun is...
Yeah, there is an answer by the Gautam Shankar. It is 2.3 into 10 power 22 second.
Okay, he has to convert it into years. Okay, 22 seconds is okay. You convert it into years.
Okay, there are some few answers are popping up. So it is 10 power 18 years or something like that.
No. So I told you we discussed in the morning in the lecture, how long the sun will live. You should get approximately that much. So what is the current age? It's about 4.5 into 10 power 9 years.
Yeah, someone has, it is 4.5 billion years. Someone has the answer.
Okay, approximately of the order of you should get 10 power 9 years. Okay. All right. Okay. So with this simple exercise, I think I'm already off. Am I close to my half an hour time? Anyway, I will quickly go through what I have given in the
you have still 10 more minutes left.
Okay, fine. What I wanted to explain. Okay, so I kind of, this is somewhat a lot of equations here. I kind of went through very fast in the morning. I told you you can derive a simple wave equation for the helioseismic waves which are trapped inside the sun. Sun is like a resonating spherical body, and the dispersion relation, which is called, which relates the wave number, okay, kr squared and kh squared. These are the radial wave number and horizontal wave numbers, and it relates to the frequencies. It is called the dispersion relation. I didn't discuss that in detail, but then the dispersion relation is given. Anyway, I will make a PDF file of my presentation. Noting this is the dispersion relation. Kr squared equal to omega squared minus omega c squared by c squared. And this is called the Lamb frequency SL squared, which is given here, kh squared, L into L plus 1 c squared by r squared. So there are certain expressions, and omega c is the cutoff frequency, c by 2h, and h is density scale height. Okay, so I given you in the Google Drive, there is a JCD model s.dat. It is an ASCII file. The README file explains to you what all it contains. Okay, so all these quantities, c by 2h, h, all of them can be calculated. So the expressions are given. You know, you have to differentiate density, logarithmic density, and inverse of that is the scale height. Once you know the scale height, and omega c can be determined. Okay, and remember this. And then this is the exercise. Okay, I will again, since I'm going to make a PDF file of this presentation. So this is the exercise you should do at home. Okay. So I described to you using these equations, that these equation basically, this wave equation here with the dispersion relation given here, basically models the paths of acoustic waves inside the sun. Okay, and the paths are given by this differential equation. So r is the radial coordinate, theta is the theta, in spherical polar coordinates, r and theta, which you all know. So the dr by d theta is related to group velocity divided by vg, group velocity, radial group velocity to horizontal group velocity. So they are defined like this. So we know the expression between omega and k's through the dispersion relation, which is shown here. Okay, so you have to calculate the various quantities using the model S, JCD model S, which I have given there, and calculate, and you simply integrate this equation, which is numerically. I hope you can do. It's very simple. I'm sure in Python one can do a simple numerical integration. And this is the expression here, and this is the problem you should do. I think I will leave that as a, you can't right away do it, but it's a very simple and straightforward thing to do. Okay, so so as a function of spherical harmonic degree L, you choose a certain value for L, and you choose certain frequencies for the omega numerically. So let us say 3 millihertz. I told you the solar oscillations are of the order of 5 minutes. So you take, say, let us say 3 millihertz corresponds to roughly 5 minutes. So you should use a value of omega equal to 3 millihertz, and L certain number you can choose. And then for that omega and L, determine the ray path inside the sun. Okay, it looks, as I explained, it may look difficult, but it's very, very simple and straightforward to do once you are able to read the model and calculate these various quantities. Okay, this thought I would leave it as one exercise. Okay, so let us go to the other one. So for example, here I have plotted, what I am asking you to plot is like this. So here, for example, I have plotted the ray path for L equal 2, and frequency nu is this is in hertz, microhertz. And there are different L equal to 2, which goes very deep, and L equal to 100 is very close to the surface. So depending on L values, you will get different wave paths. So basically, as a function of R and theta, you will find solutions. So that is the simple problem. Okay, and the other problem I gave, Okay, I think I need to explain that little more detail. I didn't cover this in the morning. Maybe, yeah, here, this is the problem. So I have given you the series of images. The FITS file, if you read tract V, there is a file with velocities, tract velocities. It's a Doppler data cube. So you can, I told you it is as a function of X, Y, and time, right? It is a series of images. Okay, you can take, it's not the whole sun. What I have given in that FITS file, if you are able to read that using Python, you will find a series of images of a square region on the sun. Okay. Okay, I will just ask you to make a power spectrum. It's very simple. Okay, you in that README file, I have given you the size. It's about 0.06 degree per pixel. So if you know 0.06 degree on the sun in heliographic coordinates, so you know the radius of the sun, so you will be able to 360 degree is full circumference. So you can find 0.06 degree what size it corresponds to. Okay, that is given in the name of the file and the pixel size. Don't use this pixel size given here. Actually, the data I have given there is slightly different resolution, lower than this. Okay, this problem I need to correct. So the correct size is given in the README file. And the time cadence is 45 seconds. The images are every 45 seconds. Okay. So you just apply the three-dimensional Fourier transform, FFT, and then determine the power spectrum, which I have shown here. Just plot it as a function of frequency, which will be the temporal Fourier transform, will give you the frequency. And here, instead of L, you will get a KH. KH is square root of KX squared plus KY squared. Okay, is the spatial wave number. Okay, so that's all. You don't worry about. I didn't teach you the time distance diagram on the right. You can just read the data cube and see if you can make a power spectrum. You will get a three-dimensional power spectrum. In the Google Drive, again, you will find a PDF file which explains to you Fourier power spectrum.pdf. So you read that PDF file. It explains to you how you can take Fourier transforms and how the kx, the wave numbers, are related to the spatial coordinates. So use that information and make a power spectrum. Okay, I think that is good enough. If you are able to get a power spectrum, verify for yourself that you will see ridges like this. Here I have plotted in terms of spherical harmonic degree L, but what you will plot is in terms of KH, because it's only a square region. So it's a plane parallel data, a small region on the sun. So again, still for that region, you will get a power spectrum of this type. Okay. All right. Power spectrum is just the Fourier transform modulus square. You just take a three-dimensional Fourier transform and absolute of that and square it. That is the power spectrum, simple power spectrum in a very straightforward way. Okay. And that's all I wanted to. How much time I have?
Yeah, it's almost over.
Okay, so before finishing, I just wanted to use this. Probably Piali also will cover. I just wanted to give a little bit introduction to IIA, the solar physics at IIA. This is a collage of pictures which shows you the history of IIA, right? From the top left to down and then right as the time progresses. Okay, the Kodaikanal Observatory is what you see on the left top. Very old picture. When the British were here, they built the Kodaikanal Observatory, and there's a picture of John Evershed. And then the series of images. We have been observing the sun at Kodaikanal for more than 100 years. The most well-known data from Kodaikanal is called the calcium K images. It's a chromospheric image in calcium 3933 angstrom wavelength. That is with the picture of that, if you follow my cursor, which is shown here. The emission in calcium K, calcium atoms on the sun emit at a particular wavelength, which you see the structure there here in the sun. So they trace the magnetic field of the sun. So for more than 100 years, we have been continuously observing, taking pictures of the sun at Kodaikanal at that wavelength. And then there are some facilities. And then there are current facilities. We plan a big national large solar telescope. Maybe next slide will show you. Okay, yeah. On the right here is a picture, a model picture, design of the what we have proposed is a big national large solar telescope, which is going to be built in Leh in Ladakh region. And then we are also part of a space mission. It's called Aditya L1 mission, which ISRO is going to launch next year. And we are building an instrument for that. It's called VELC. And these are the two major projects which IIA is involved. There is one space mission and a ground-based big solar telescope. And then we are also doing helioseismology, and there is a radio observatory which is shown here at the bottom, and Gauribidanur, a place called Gauribidanur, to observe the sun in radio. So these are the various activities. So these are the research areas at IIA. The number of people, faculty is about 13, about PhD students are about 50. So the various areas of solar astronomy we do here. And these are some more pictures of Kodaikanal and Leh. The Pangong Lake is the identified site. I hope most of you know about this lake, where the Chinese were, confronting us there. So this site, this is called the Pangong Lake, is very close to the Chinese border, but still the government has given a piece of land there to Indian Institute of Astrophysics that is there in this picture. It's a small incursion site. It is next to a village called Merak in Ladakh, on the shore of Pangong Lake. So there we have already set up some facilities there. So the NLST project is going to be, we hope it will be approved soon. And yeah, I think I will stop here. So this is the team involved in the VELC project. It's called Visible Emission Line Coronagraph on board Aditya L1. Aditya L1 is the mission, ISRO mission, which is going to a point called L1, Lagrange point 1, which is the point of equal gravity between Earth and the Sun, which is about 1 million kilometers from the Earth towards the Sun. So that's where this spacecraft, Aditya, will be stationed. We will launch, ISRO will launch it towards L1, and it will go and orbit this L1 point. It is so it will be continuously watching the sun from this point. So in space mission, IIA is building a instrument called Visible Emission Line Coronagraph, VELC. It will make an image of the corona, which I think Piali talked to you about. Coronagraph, which will image the corona. So there's a large amount of activity involved with that at IIA. And this is the NLST project. All right, I think I will stop here. Vasantaraju, are there any questions?
As we are running late, shall we keep our questions at the end of the session?
Oh, fine. Okay.
Okay.
I will stop sharing.
Professor Piali Chatterjee, you can share your screen.
Yeah, okay, I'll do that. Okay. So, yeah, so I think I was looking at these some of the questions from the last session, which I don't think I have answered sufficiently because some of the material was going to be covered later on. So I just noted down some of these questions. One of them is, I think it's more a question for Rajguru than me. But the question is, why is the information gathered from neutrinos produced in the sun different from the information gathered observing it in other means?
Oh, so, sorry. Can I just comment on that? I didn't even touch that neutrino, solar neutrino problem. I didn't. Probably I had one slide which talked about that. As a success of helioseismology. Solar neutrinos are, I don't know, what is the exact question? Why is the information gathered from?
Yeah, the question says, why is the from neutrinos produced in the sun different from the information gathered observing it by other means. So maybe what he means is that these other wavelengths we are observing it, imaging and spectroscopy, why is that information, or how is that information different from the neutrino information?
Oh, okay. Okay. Anyway, so we didn't talk about this, but anyway, I'll just give you try to give a short answer. So the solar neutrinos are byproducts of the nuclear reaction, which I talked about. When the protons and protons collide and fuse and produce helium, they also release some neutrinos, which are the nuclear physics involved is very well known. Given the information about the conditions inside the star, you can determine how much of neutrinos will come. But if you can observe the neutrinos, I don't know what the question exactly refers to. So there's something called solar neutrino problem. The amount of neutrinos we have detected generally is only 1/3 of what we predict through the model, through the nuclear reaction which is happening in that. So that is called the solar neutrino problem. I don't know if that question is related to that, but then that neutrino problem has been solved. So the reason is that we are observing only 1/3 of the neutrinos because the neutrinos change flavor. There are 3 types of neutrinos from they travel from the sun to us, and they change into different types. So we are not, if you measure all the different types of neutrinos, then there is no problem. Okay, so that is so why is this information different? So this information is directly tells you about the core.
The interior of the sun.
Sorry?
The interior of the sun, whereas
it tells you the interior structure where the nuclear reactions happen. So what we know is currently what we have built as a so-called standard solar model, which I explained to you how we build it. It is pretty accurate, and the neutrinos, the additional physics, which is that the neutrinos change flavor among 3 types of neutrinos. If you put that particle physics into the picture, it is consistent with what we do. Okay, so that's all. I hope.
Yeah, and maybe Rajguru, you have already covered it. Just to emphasize that, correct me if I'm wrong, the nuclear reactions are only occurring in the core of the sun, right?
Yeah, right. Yeah, so maybe it's only occurring in the core. Yes.
It may not be clear to some other people that that's why it is only sampling. The neutrinos are only sampling the core of the sun rather than any other parts of the sun. Is that correct?
Reactions, hydrogen fuses only in the core within about 0.2 times the radius of the sun, within that. So basically you need several million degrees for the hydrogen protons to fuse. And that happens only in the core.
Yeah,
okay, go ahead.
Okay, yeah, thanks Rajguru. So there was this other question, I think I tackled it partially. Are prominences also eruptive like flares? How do we differentiate them? So Ashwati, the prominences are also eruptive like flares, because the reason the prominences erupt are because there has been a flare just above it. So that's the reason the prominences flared. So to answer your question, I just have this simple slide here. So you see that there are these field lines, these loop-like field lines here, and these have a twist-like structure. So if you observe it from one particular angle, these field lines actually have these dips, and in these dips the material can lie. Like I was talking about this hammock. So this is the filament material which is cold, and it is cooler and denser than the surrounding. So that is the filament. So if this flux rope in which this filament is suspended erupts, like you see in this movie below, the filament is also forced to erupt along with it. So the flare is the reason for the filament eruption. But also remember that not all flares will have filaments associated with it, because filaments normally form in the solar atmosphere because of what is known as thermal instability, some kind of a thermal instability, or also known as condensation, plasma condensation. So if the conditions are not ripe for filament formation, then if you have a flare and the flux rope doesn't have a corresponding filament, there will be no filament eruption. So the filaments just lie, you can see on the right hand side, this again, this volume rendering plot here, that this green, yellow, red, this part is a filament. It has been colored by its some vertical velocity, never mind that. So it's just sitting there quietly by the support of this flux rope, so waiting for this flux rope to erupt. So whenever this flux rope erupts, the filament will also erupt along with it. And I think there was another question. What happens when solar flares collide with the Earth's magnetic field? Okay, so let's go on to that space weather aspect of coronal mass ejections. So this is a movie of coronal mass ejections that occurred during 1 month during a solar maximum. The solar maximum is typically, it would last 2.5 years. And it is only 1 month. So you can see during a month or so, you can have around 200 or so CMEs erupting. So this has been measured by a coronagraph known as the LASCO C3 coronagraph on board SOHO. So SOHO is also a satellite which is still working, probably some aspects of it, at the Lagrangian L1 point of the sun. And Rajguru also mentioned that India is going to send its first solar satellite to also the Lagrangian point, with a much better coronagraph, much better designed coronagraph known as VLC. And we can hopefully have, which can observe the coronal mass ejections much closer to the sun. I mean, much closer to this white circle here. So the radius of this white circle here is about 1 solar radii, whereas this disk that you see, the occulting disk, is about 3 solar radii. So, VLC, the coronagraph Rajguru was talking about, is the radius of it is about 1.05 solar radii. So we can observe the coronal mass ejections, the dynamics of the coronal mass ejections much closer to the solar disk. So, so this is a short fact sheet about CMEs. So these are basically magnetic clouds, magnetized clouds of gas, which are ejected from the sun at really large speeds, ranging from 300 kilometers per second to more than 2,000 or 3,000 kilometers per second. And since I spoke about these slow, fast, and Alfvén modes, so the Alfvén wave speed, I also defined the Alfvén wave speed in my last lecture. So sometimes the Alfvén speeds in the solar corona are less than the speeds of the coronal mass ejections, which means that these coronal mass ejections can have super Alfvénic speeds, and hence they are really, really energetic. So those kind of CMEs, which are also known as fast CMEs, they produce shocks and synchrotron radiations, and they cause radio storms on the Earth. So these CMEs can, depending on their speeds, the CMEs can be classified into slow and fast CMEs. So they have to be slow and fast compared to something. So here that something is the solar wind. So the solar wind speeds are typically of the order of 400 kilometers per second. So CMEs which are slower than that are known as slow CMEs, whereas CMEs which are faster than the solar wind, so for example, a CME which has a speed of 2000 kilometers per second will be called a fast CMEs, because the solar wind speed is much smaller than that. So here fast and slow has nothing to do with MHD modes, but it has to do with the speed of the solar wind. And these CMEs can also produce energetic particles, because if there is reconnection associated with it. And also in the shocked regions, the CME can produce shocks. In the shock region also there can be energetic particles which travel at the speed of light. So they'll reach Earth in 8 minutes, whereas the CME would can take 12 hours or up to a day to reach the Earth, if it is Earth directed at all. The CMEs that you saw in this movie, well, none of them were they were all going out in the plane of the sky, so they were not Earth directed. The Earth directed CMEs in the coronagraph will look like halos. Okay, so this is a cartoon of a typical CME morphology. So the CMEs have this light bulb kind of a structure. So they have this sheath, the bright loop, and then they have a bright core and they have a dark region here. So if you look at this, a more simpler cartoon, so you have the prominence material, which is this bright region. So it is bright because it is dense. So the amount of Thomson scattering occurring here is more. I mentioned Thomson scattering in my last lecture, if you remember. And then this is the cavity made up of the magnetic flux rope. So that's why it's dark, because the density is less there. The material is less, so it is dark. And outside this cavity, there is plasma pileup. And then there's this plasma pileup because of the shock, right? And then there's a shock front, which is going, propagating up. So not all CMEs have all these three structures. Usually the fast CMEs would have all three structures. And presence or absence of the filament can determine if it has a core or not. So there can be filament-less CMEs, which won't have a core. And if there's a filament, then it will have a bright core, right? So that is typically, this typical three-part structure of a CME. And then there was a question about these, about how these, what happens when solar flares collide with the Earth's magnetic field. So here I basically borrowed some movies from the Wikipedia, but these movies are really nice. And these are some simulations that have been performed using NASA's community modeling code called BATSARAS. So this top movie here is from a regular X-class flare, which happened in, say, December 13th, 2006. So this process. So if I run this, I'm sorry, I don't want to. Sorry about that. So let me try to explain what's happening. Yeah. So you have this regular CME. So you have this Earth's magnetic field. You can see Earth's magnetic field, and then there's this magneto-tail, and then you see this bow shock region. And now there's a regular CME which hits the Earth's magnetosphere, and look at what it did to the magnetic field of the Earth. So if the Earth did not have the magnetic field, you would understand that most of the atmosphere of the Earth would be, evaporated away. So thanks to the magnetic field of the Earth, we, our planet is able to sustain life and hold on to whatever atmosphere it has, unlike, for example, planet Mars. So this movie will run again, and you'll see that there's this CME hitting the day side. So this is the day side, this is the night side, and then hitting the day side part of the, and then there are these reconnections occurring in the magneto-tail at the night side. And because of this reconnection, you will again have energetic particles entering the Earth's atmosphere through the poles, through the north and south poles, and giving rise to these northern and southern lights, the auroras, what they are known as. Now, there was once this flare, a recorded flare in history, known as the Carrington event of September 1, 1859, because this was observed by the British astronomer Carrington. So it was a very bright flare. So this flare was even visible over and above the disk light of the sun. It was like so powerful. So what these people at NASA did was they simulated what would have happened, or what had happened to the Earth's magnetosphere, because this Carrington event was a geomagnetic event. It did hit the Earth's atmosphere. And what did happen in 1859, and what havoc it may have caused if we had this anthropogenic systems like satellites and things like that. So you can see what you can see how it compares. Like it's just all washed out, right? So they would have had spectacular auroras, and apparently there are in the news about auroras being observed almost to the near the equator. I mean, it were like so powerful. So this is what the geomagnetic superstorms can do. But it's not that we have such storms every day. So we haven't had a Carrington like event since 1859. Maybe it's due, but we don't know. But all we have for now is regular size X class flare and fast CME events, which are not so disruptive as the Carrington event would have been. So
yeah, there is a quick question.
Yeah.
If you want to take.
Sure.
I mean, so there is some kind of a confusion in the participants. So could you please clarify that what do you mean by solar flares, prominences, CMEs, like that? So again.
Okay. So yeah. So these prominences is not an event. It is a feature on the sun's atmosphere, which is basically the material which is resting by the support of the magnetic field. So the prominences can erupt or it cannot erupt. Whereas flares and CMEs are eruptive events. Right? They are events. Prominence is not an event. It is a feature that you see. Like mountain is a feature that you see on the surface of the earth, right? Whereas a volcanic eruption is an event, right? So that is the difference. I hope that makes it clear. So volcanic eruption is an event, earthquake is an event, but a mountain or a volcano itself is not an event, right? It is a feature, right? So when I say flare, what I mean is there is magnetic reconnection, and that is releasing the energy. When I say coronal mass ejection, I only mean that there is some magnetic cloud which is being erupted out of the sun. Often the reason this magnetic cloud is ejected is reconnection, but not always. It can be a result of other instabilities, other MHD instabilities, but I'm not going to focus on those because it's a very so the idea of this kind of a lecture is just to motivate you about what kind of dynamics goes on in the sun. So CMEs and flares are two different kinds of events. In the flares, you have magnetic reconnection, and as a result of it, there is a lot of electromagnetic and high energetic particle released, electromagnetic energy and high energetic particle which are released, and they reach the earth in about 8 minutes. That's the time light takes to reach the earth. Whereas in case of a CME, other than the solar energetic particles, you also have a magnetic cloud, and that magnetic cloud is going to affect the Earth's atmosphere in such ways. It can disrupt radio communication, because once the magnetosphere of the Earth is affected, it also sets up currents in the ionosphere. And ionosphere is responsible for reflecting the radio waves, right? So the radio communication, for example, you use radio communication or microwave communication for mobile phones, or even when the airplanes fly, they use this radio communication, right? So all these things can be disrupted because of induced currents. And if you have, for example, astronauts going to space, so then they can be affected because of high energetic particles, because of the flares as well. Whereas so these are basically the outcomes of the flares and CMEs that we have on the Earth's atmosphere. But they are two different things. They can be related. Like often a CME can have a flare associated with it, whereas there can be CMEs which are flareless. There are no flares, but you still see a magnetic cloud. So that's why I say that there are two different things, but these are events. These are not features on the surface of the. They're not always present. It's like a volcanic eruption, an earthquake. It doesn't happen all the time, but it happens sometimes. So is that sort of clear now?
Yes. So there is another question: why CMEs don't happen in the polar latitudes?
Okay, the CMEs can happen in the polar, what are known as the inversion lines or H alpha filaments in the polar crowns, right? So, but then they are not related to active regions. So most of the CMEs whose origin is above the active region, I told you that the most of the flares and CMEs take place above the active region. So the sunspots only form at lower latitudes. Like there's this band plus minus 40 degree latitude, north and south, within which the sunspots form. So if the flares and CMEs are sunspot associated, then they are confined to only those latitudes. But CMEs can actually occur there can be polar CMEs, not exactly at the north and south pole, but in a region known as the polar crown filament. That is where, that is where the magnetic field changes sign during a dynamo cycle. So I'm sorry, I don't have slides for that here, but it is possible to have CMEs in latitudes as high as, say, 60 degree or something like that, but definitely not in the 90 degree, because occurrence of CMEs and flares need this change in magnetic field. The magnetic field should be changing spatially and very drastically. So you don't have sunspots in the poles, and also the polar magnetic field is more or less, dipolar. So uniform dipolar. So that's why it is very difficult to have CMEs, above 75 degree latitude, for example. But you can still have CMEs at higher latitude. So any more questions, Vasant?
Yeah, no, please go ahead.
Okay. So this is the next slide. So this is an example of CME interactions. So often you have, multiple CMEs being ejected from the same region, or what are also known as sympathetic eruptions. I think I mentioned that those in the passing in the last lecture. So what would happen is there is a CME which is, slowly making its way out into the heliosphere, and all of a sudden from behind there comes another CME and pushes it. Just like a collision of cars, God forbid, on a highway, for example. And then there's the CME interaction. So those interactive CMEs are also a phenomena which is of very much interest for what is known as severe space weather, because they trigger a special kind of radio storms known as enhancements. Some enhancements which can be detected by these spacecrafts, wind, for example, wind spacecraft, which is in the heliosphere. So this is another example of interacting CMEs. So this is a famous Halloween storm of November 2003, where there were like some radio blackouts and stuff like that. You also see enhancements here. So there was a slow CME. This is a CME which is, trudging ahead, and all of a sudden there is a more energetic one which goes and gobbles up the slower CME. So the second CME is usually the faster, and then it goes and kicks the slower one and interacts with it. And this combined ejecta can be much more geo-effective. So from space weather point of view, these are like very interesting candidates. So sometime back, we developed a model of, such interactive CMEs, and we focused on what are known as rotating sunspots. So often you see sunspots which rotate, and they are a signature of twisted magnetic field lines in the solar atmosphere. And those rotating sunspots, I mean, you can see this cyclonic sunspot here, big sunspot, below an even bigger sunspot, which is like rotating really fast. And it sort of rotated by, about 100 degrees in about 3 days or something, which is actually very fast for, solar length scales and time scales. So which means that it gathered a lot of twist along with it in the magnetic field line. And more twist the magnetic field lines have, they are more likely to store, a lot more energy that can be released. We just did this, computer simulation of, it's a very simple simulation of a flux rope, which is emerging into the solar atmosphere. And then because of ideal MHD instabilities, they erupt. So you see this flux rope simulation. So this simulation has been performed by solving MHD equations. It is not not just a model. It is by solving this set of MHD equations where we apply this emergence of a flux rope here. And on the right hand side, you see the velocity with which the flux ropes are ejected. So initially it is like really slow. The emergence is really slow, and then they go put like a volcanic eruption. So that is one of the models of how CME is formed. So this is what, again, we go back to the question on CME's influence on space weather. So they have, a large plethora of effects that you can see. So you have there are these oil pipelines. So there can be these induction currents induced in them. And if there is fuel in that can catch fire, for example. And then there can be these airlines which fly the polar route. So often to save aviation fuel, if you want to travel from, say, India to US, there are a lot of flights which take the polar routes. So rather than flying over the Atlantic, crossing the Atlantic, they take the polar route. And in 16 hours you can be in California, for example. So those polar routes are really affected because most of the energetic particles are entering the Earth's atmosphere through the poles. So that is, they affect the radio communication here. And then, of course, if you're outside the Earth's the ionosphere, atmosphere of the sun, then there is nothing to stop these energetic particles, and they can damage your solar panels, for example. So if the spacecrafts don't, they protect their solar panels in time or shutter their telescopes in time, the instruments inside can be damaged. So this is just a cartoon, not a cartoon, this is from a simulation, from the simulation I showed earlier, of how a magnetic cloud can look from two different angles. And you can see that it is still tethered to the sun's surface, but it is like, huge as it travels out into the heliosphere. And they also form auroras. So the auroras are formed when these energetic particles are entering the Earth's atmosphere, and then they're interacting with different atoms in the atmosphere. For example, an oxygen atom would glow red, a nitrogen atom can glow blue or green, whereas depending on the height of the atmosphere, so if there are nitrogen molecules, they'll glow crimson. Whereas if they're nitrogen atoms, they can be green or blue. So you have these different dancing patterns in the auroras, right? And aurora is not just observed on our planet. So this is a picture of an aurora from space, but on other planets like Jupiter and Saturn as well. This you already know. And here, let me just reiterate what Rajguru also mentioned about, the kind of solar physics that is being done and has been done at IIA for over a last century. So there are these two very promising upcoming projects. One is already in the making, the Aditya L1 satellite, the space-based satellite, for which at IIA we are building the team. There's a team at IIA headed by Professor Prasad, who is building this VLC instrument, the coronagraph, visible emission line coronagraph. And then there's this 2-meter class National Large Solar Telescope. The images I was showing earlier of the sunspot was from the Swedish Solar Telescope, which is 1-meter aperture telescope. So this one is going to be a 2-meter class telescope. And then there's a century-old archive of white light and calcium to full disk images taken from the Kodaikanal Observatory for last 100 years. So every day there has been an image taken in white light and calcium-2 full disk image, and in which you can see a lot of features like active regions, like sunspots and plages and filaments and things like that. So it's a mine of data for last 100 years. So you can at least 10 solar cycles you can study using this data, and it is all available online for people to download and look at. So a bit more about this Aditya L1. So Rajguru also mentioned that this satellite is going to be at the L1 Lagrangian point. This is Earth and this is the Sun. And it will have the same orbital velocity as the Earth, which means that it's always looking at the sun 24/7. So there are a lot of instruments on this satellite. There are 7 payloads. 4 of them are remote, basically imaging instruments, and there are 3 which are in situ. So it is going to measure the condition of the plasma, the space plasma at the L1 Lagrangian point. So since we are building, IIA is building this instrument, so these are some of the scientific objectives, like the diagnostics of the corona, how the corona is heated to 1 million Kelvin, and studying solar wind acceleration and large scale transients like CME and jets. So this is a very unique payload because we can measure, we can take images at high cadence and high spatial and spectral resolution. It is possible to do simultaneous spectroscopy and imaging. And as I also mentioned, that observations very close to the solar limb will now be possible. And we can also do, with some effort, we can also measure the line of sight magnetic field in the solar corona, make an estimate of magnetic fields in different regions, and gather about the direction of magnetic field in the plane of the sky. The other one is this NLST, National Large Solar Telescope, which is going to be installed soon, hopefully, at Pangong So Lake. So in the incursion in the Pangong So Lake, and this is an picture of how the dome, the dome structure of the telescope here. And this telescope actually fills a longitudinal gap for different other ground-based telescopes. So you have this telescope in Hawaii, and then you will have DKIST, BBSO, the Big Bear. Then you will have this La Palma, the Swedish Solar Telescope, and then we have this VLC in Ladakh. So this basically fills a longitudinal gap. So this curve is basically the day-night separator here. So you can see that it is possible to, if it is possible for these ground-based telescope to tie up, then we can have very good high-resolution ground-based data, from different regions at all times. So the sun will never set on this network. So these are the broad scientific goals of NLST. Basically, it focuses on high-resolution observations. And then at resolutions which are less than 70 kilometers on the surface of the sun. And then we have these study of different MHD processes and waves in the photosphere and the chromospheric region, because that's what we can only observe from the ground-based telescopes. And this is what is upcoming, and what is so exciting. And this is a very good time for people in India to come to solar physics, and especially to IIA. So with that, I would end my talks. If there are more questions, if there is time, then I can take.
Yes, there are questions. So there is a question from Megha Vaibat. She is asking about what factors affect the thickness of coronal loops.
Okay. So the problem of why coronal loops exist isn't still an unsolved problem, right? It is so So this is an unsolved problem. So what affects the what I have seen in literature is because of what is the region where heating is taking place. So the loops are bright regions, right? So they are like regions where heating is taking place. So that's why the loops appear thin. So these loops are not necessarily magnetic flux tubes. So the magnetic flux tubes in the atmosphere would be, for there the thickness would be determined by the pressure balance between the gas and the magnetic pressure. The magnetic field also exerts pressure. So the balance between the magnetic pressure and the gas pressure will determine the thickness of the magnetic flux tubes. But these loops are not exactly magnetic flux tubes. So their thickness and why they are bright and their structure is still an unsolved problem in solar physics.
There is another question by R. Gopal. He is asking how CMEs affect satellites.
Okay. So CMEs with them would carry these highly energetic particles. I mean, not with them. Because of the CME, there can be these highly energetic particles. And then those, I showed you this movie, right? Yeah. So for example, you saw this these movies, right? So here there would be even before a CME has hit, high energetic particles can hit the satellite's electronics, their electronics and optics, and then they can be damaged because of all these currents, and then this the detectors can be damaged, and things like that. So maybe people who do instrumentation can answer this question more specifically, but I can tell you it is because of these high energetic particles. Yeah, next maybe.
Yeah, there is another question. Okay, I just somewhere it is gone. Yeah, there is a question by Akash Kumar. Is it good idea to detect the CMEs from Mercury because it has its magnetic field is very small?
Mercury. Oh, you mean the planet Mercury?
Yeah, planet magnetic field is very small. So is it good idea to detect CMEs if you have some kind of a instrument over at Mercury?
Okay, so yeah, for example, now we have this Parker Solar Probe, right? Which is so the Parker Solar Probe, if you look at the orbit of it, it is going to, it has a variable orbit around the sun, and at its closest approach, I think it is going to be even closer to the sun, much closer to the sun than Mercury. So that instrument will actually give us the in situ properties of the plasma at a distance from the sun, which is much closer than Mercury. But I don't know, I mean, if anybody has ever thought of installing any telescope or satellite around Mercury to measure, or if even that is possible or not. I have not seen any such proposal or any such satellite being planned around Mercury. I mean, Parker Solar Probe is one such thing, but it is not related to Mercury. It is doing its thing around the sun. And at its closest, it will be inside the orbit of the Mercury around the sun.
Okay. So there is another question related to this. Does the Earth's atmosphere provide sufficient shielding from CMEs? So you have already mentioned it actually.
Yeah, well, I mean, so far, yes. I mean, as long as the Earth, the geodynamo or the Earth's magnetic field is, working well, and we are able to maintain this magnetic field, the Earth is able to, the geodynamo is able to maintain this magnetic field, I think we are more or less, safe from even magnetic superstorms, because the superstorms that you see in this movie here are not going to occur so often. So I think we are more or less safe. But there are these studies on other planets like Venus and Mars. For example, Mars had probably life. It is said that probably had life earlier. Now it doesn't because its magnetic field is dead and things like that. So it might happen that the geodynamo, something happens to the geodynamo, it goes wrong, and then our magnetic field is not strong enough. But yeah, we hope that doesn't happen.
In the same line, how to protect satellites from CMEs?
Okay, so the only way is to shut the instruments down on time. So you have to shut down the photoelectric, not the cells which take the sun's energy and convert it into electricity. Those panels you have to shut down. You have to shut down the electronics. You have to put the shutter in front of your camera, in front of your telescope and things like that. That is the only way to. You cannot move the satellite away from its orbit. So that's the only way to shut down the satellite and just wait for the storm to pass.
Yeah. With that, if you have time, you can go through the chart. So Professor Rajguru has something to present on the Google Drive.
Okay, so shall I stop sharing then?
Yeah, please unshare it. So
okay.
Okay.
Yeah,
Professor Rajguru can share.
Yeah. So I just wanted to a little more explain to them, because there are more files than what I explained in my presentation so far. So the Google Drive, as you can see here, I hope all the students are there. So this is the Google Drive. I have put a set of files. There is one file, the first one you see there is Fourier power spectra.pdf. So that explains when you take a FFT. I assume that all of you know what an FFT is, fast Fourier transform. So there's a single command you can call in either in Python or any other software you use to take fast Fourier transforms. It's basically discrete Fourier transforms you can take calling a single function. So it explains how the Fourier spectra, are related, the wave number and other frequencies, how the basically the theory behind the Fourier power spectrum is explained in this PDF. And then this JCD model, S.dat is the solar model as a function of radius, various quantities. So this is explained in the README file. And forget about this PKH. There are a set of, there is one profile, there is a program, it's an ideal program file. I don't know how many of you use Ideal. Ideal is a software called Interactive Data Language. It is a licensed software. You may not have access to it, but there is an open source version of Ideal. It is called GDL. You can GNU DL. It is the open source version of Ideal. It's called GDL. You can look up, you can install it in your laptop and try to use this program, read JCD model S.pro, which basically reads this JCD model S.dat. JCD stands for Jorgen Christensen Dalsgaard, the name of a scientist, a solar physicist, on whose name is this model is usually called. It's called Model S, standard model of the sun. JCD is Christensen Dalsgaard is a well-known solar astronomer. We usually use his model as the reference model for the sun. Basically, the run of various quantities of the sun as a function of depth or the radial coordinate inside the sun. So that is explained in the README file. And then these files called tracked, this one here, these bottom three files are fixed files. Tracked B is the last one, and tracked M and tracked IC. So these are three quantities, three physical quantities. Tracked V is Doppler velocity. Tracked M is the line of sight magnetic field. And tracked IC is the continuum intensity. So all these three data, it's a FITS file. It's called a flexible image transport system. That is the typical astronomical standard we use. It is a typical way of writing out large data in a particular format. You can again search in Google what is FITS. There are a lot of standard routines for various platforms available to how to read these bits files. So I asked you the exercise, I asked you to do the power spectrum, to estimate the power spectrum from a series of images. It uses the Doppler velocities. These are called Dopplergrams. It is a small region on the sun. So all these three data sets in FITS file are observed by the Solar Dynamics Observatory. There is an instrument called Helioseismic and Magnetic Imager. It produces Doppler velocity and line of sight magnetic fields, as well as the continuum intensity next to a particular line. So you can read these files. I know you can just play around with the data. You will learn a lot by just looking at how the Doppler velocity looks. So this is basically about, as I put in the README file, it's about 1 full day of data every 45 seconds. So you will have roughly about 1,000, nearly 1,100 something images you have, nearly 1 full day of data of a small region on the sun. So you can, for example, read all the images. For example, you average all the images in Doppler and then display it, and you will learn what it shows. If you average over the full period, then you will miss all the oscillations. You will only the background convection and rotation you will see. So you can try to identify what is the rotation signal and what is the convective signal there. And then you subtract from each image the average of this, then you will see these oscillations. So then you can display them, plot them, and see, you take a particular pixel as a function of time, you plot, you can do that. And then you do it for all the three variables. Continuum intensity, how the light looks for that region, and then how the magnetic field looks for that region. Okay. So all of this you can play around with. So these are huge data files. Each one is about a GB of data. I hope you can download them to your laptop or a desktop which you have, and download a software which you can read the FITS files and then play around with it. And then try to do the exercise I showed you in the lecture. So building a power spectrum using this tracked B data. So tracked means we track a region on the sun. So this particular image in each stack of images are all produced after tracking a particular region. As the sun rotates, you need to track that particular region. So the physical region on the sun is fixed. So that's why it's called tracked. So since when you continue to observe sun is rotating, so the region will move out in coordinates. So we track them and then align them and make a data cube. That is what is done. It's already a processed data, ready to use data of a small region on the sun in velocities, magnetic field, and intensity. Okay. And I hope you can play around with it and then do the exercise I just gave you in the lecture. Okay. And then, that's all I wanted to explain. I hope if anybody has any difficulty in, reading FITS files, you can just Google. It's all, you're all, these days, everybody, a lot of young students, you're all should be well possessed to, Google and do this, install the necessary software to read the FITS files. All right, I think that's all I wanted to say. If you have any questions, yeah, put them in chat box or write to us an email. I hope all of you know individual emails. If you have any specific questions on the lectures, you can write to us as emails also to the lecturers. I hope you have access to our emails, or you can find it in our website. All right. Okay. So that's all I wanted to say.
Yeah. Thank you, Professor Rajguru, and thank you, Professor Piyali Chatterjee. And this means if you have time, please go through the charts because we have missed so many questions. So if you have time, kindly answer them. And over to Professor Pravabati, if there is any announcement, please.
Yeah, I would like to make some announcement, and that is regard. So a lot of people have been asking for the material for the, like, for example, what Rajguru just talked about, and the slides for the lectures and so on. So we are planning to put them up on the summer school webpage. So the page is almost ready. It is not yet up, but by tomorrow morning it will be up. So you can please keep looking at that page from time to time, because the tutorial material and so on will be uploaded there, and you can download from there and work with that. So it is uploaded there. I have also emailed, of course, but uploading there is better for people on YouTube also. So everybody can download from that page.
So I will, just Prabha, I will put my presentation in the Google Drive folder I created for my tutorial.
Okay. But that is, yeah, so you put it there. So I have emailed it to the Zoom participants. Yeah. But for the YouTube people, there are questions from the YouTube people also. I think there are several who are keenly following the lectures. So for them, we will put on the webpage, and they can get the link will be there, and they can download from there.
Yeah, sure.
Yeah. Okay, so I hope everybody had a good time today. So I think we can close the session. Yeah. We meet tomorrow at 9:30.
Thanks, Prabha and Vasant, for coordinating this.
Yeah, thanks, Piali. Thanks to all the speakers actually today. Very good talk.